This video is going to be all about understanding blueprints, reading them, figuring out how to inspect based off of the requirements. I usually say your decision making when you're using all the gauges that we're covering in this video series, your decision should be based on the blueprint requirements and the tolerance size. So if you're not familiar with blueprints, if you're just starting out in your career, this will be a introductory video on how to read them, how to interpret them, and what you should do in certain situations. What these different symbols mean. There's a lot to reading these. There's a lot of effort that's get put in to making blueprints so that uh, the person making the part, the person inspecting the part, can do the job completely from start to finish without any communication with the person who drew it. That is the intent. So in this video series, or in this video today, we're going to be working with this print you see on the screen. You can find this print on the Pragmatic Metrology website. So please, before you continue, go download this print and follow along. Maybe print it out so you can see the print as I'm discussing the video. You can find several prints there that we're going to cover in this video series. One for the angle block, one for the step shaft, and one for the hole pattern. If you don't have, if you want to follow along with your own print and compare side by side with what I'm showing you and what you're seeing in your job, feel free to grab one of those as well. You can also find the CAD model for this part if you want to make it. You don't need to make it for this video, but if you want to follow along with some of what I'm doing, you could 3D print this. You could machine it yourself if you like. So why don't you go ahead and do that right now. But once you have that ready, we're going to get started and jump into a quick outline of what we're going to cover. So we're going to go basic overview of every piece, every section of prints, the title blocks, the drawing views, the notes, the revisions, so that you understand what everything is telling you. And then we'll talk about sort of the designer's intent and the contract. This kind of goes into some discussion about why we use prints, what they're for, what their purpose is in manufacturing. We'll go over some important steps for you to cover each time you're using a print, and then continue on with some interpretations. So I won't go into great depth on GD&T, control frames, or holes, or the other things listed here, but I will discuss how to interpret them at a basic level and what the next steps are going to be for you. So interpreting hole inspection, GD&T, some of these other ones are going to be separate videos that take too long to cover in this one. And then finally, we'll go over a few best practices when you're using these prints. So grab your print and let's get started. So one of the first things you should look at when you're starting off with a print is the title block. So the title block is going to have a lot of information that you need and some that is just for reference. When you're looking at your print, it should typically be on the bottom and starting off in the bottom right corner and moving over to the left. Now, every company's got a different policy. There certainly are standards that are published for basic structure that companies are encouraged to follow because it makes coordination between vendors and suppliers and buyers and sellers, customers. It makes all that a lot easier. So there are some standard formats out there. Some of them are country specific and some are international, but generally speaking, the print that we're going to talk about today follows the standard structure with the title block in the bottom right. So when you look at the title block here, there's a few key pieces of information such as your drawing number and your revision. You always want to verify that the drawing number you have and the revision that you have match what you're supposed to be inspecting or supposed to be making. There are mistakes every day concerning about, a revision was made but it wasn't properly communicated. Sometimes it's not properly communicated to quality control or machining or programming or the vendor. So double check that whatever requirements you have that are with your part are matching in terms of document number and revision. Mistakes happen. A lot of places make very similar parts that can get mixed up. Visually, you can't really tell them apart until you start measuring. So be sure to verify that at the very start. Then you have a part name and a description. which just helps you discuss the part. Instead of using all these drawing numbers, you can actually use something more tangible to discuss, angle block and description of what it might be. So just that just helps you talk about the parts. Then you have a sheet number. So in this bottom corner on this PM02 drawing, have the sheet number down here, and always quickly verify you're not supposed to have another sheet. Maybe you've gotten one sheet and you're supposed to have two. If you don't have the second sheet, you have no idea what's on it. Could be more requirements, could just be extra drawing views that somebody thought you didn't need, but always verify that you've got that second sheet or however many sheets you need. Next up, the dates and the signatures. So that'll show up right here in this box. There's a few different ways to designate, who drew it, who designed it, who approved it, who revised it, and on what date. For this example print, I left it probably basic, extremely basic, and less detailed than you're going to see in industry. You're probably going to see more fields and more specific dates rather than just a year. So I just wanted to keep this pretty basic and keep it clean, not focus too much on making it too complicated. When you go into industry, I guarantee it's going to be more complicated than you're seeing here on the screen. But you just want to check, what date did the print come out? Has it been revised? That goes into, do you have the right revision? Was the recent revision communicated to manufacturing? Sometimes you have a job traveler, travels with your parts, has, production information, and it was released, let's say it was released in January, and the revision for this part came out in February, and you're inspecting it in March. And some companies, maybe the new revision gets put out in February and overrides what the prints that were released in January when the part was made. So if you follow that along, what can happen is you'll get a difference. The parts were made with Rev A, they're going to be inspected to Rev B potentially. Hopefully this situation doesn't happen, but you want to keep an eye out for that sort of thing. If something was released very recently, just make sure the part matches the revision that was that you're inspecting against. Then you have a few other fields. We'll continue on with the material. So in this print, material, aluminum or mild steel. It'll be a very basic, usually just description of the material, and it could have some specific material types like 316 stainless or 304 or 4040 aluminum. I'm not an expert on all materials, but you may have some more specific requirements for your material. And when you go to verify that, in most cases, you will check that the certification for the material matches the material on this print. Not every place has the ability to actually verify the material that came in, so you're relying on if this call out here matches the material certification. Let me fix something real quick with the presentation. Yeah, hopefully now it won't disappear. So next up we have finish. So the finish can appear in different places. On this sheet itself, there's not much of a finish, like a tumble finish or a coating or anything like that. You will see in the dimensional block here, it says all surfaces RA 125, break sharp edges. That's a pretty common requirement for machine parts, but if you're working with plastic, if you're working with a different process, it may have a different finish. So this title block, as I said, a little simple. I don't, for this part, for the parts I wanted to teach with, I didn't want to put a crazy finish requirement. I just wanted something basic. So it's probably something that was, left out in this particular case in the video series. I wish I had maybe put a tumble finish or maybe a coating just as an example, but that's the type of thing you might see in terms of finish. And you'll have applicable general standards and guidelines next. So many prints will use GD&T, and they might list what version of GD&T they're using. So ASME, actually I can't remember which one it is, releases GD&T standards for the United States, and the previous revision to 2018, I believe, was 2009. Someone can correct me on that. And before that was 1994. So you will see a lot of prints specify which version they're using because this GD&T interpretations have changed over time. If you're not sure what GD&T is, I've mentioned it a few times now. I haven't explained it. It's a set of symbols that control features. So as an example, you might see a symbol that's shaped like a circle. And when you see that symbol, it's controlling the shape of your diameter. So basically the maximum error that is allowable is, maybe 5 thousandths. And what that means is it can be, kind of elliptical or egg shaped, but to a maximum of 5 thousandths. When you see more than that, then you are out of tolerance. There's many symbols. We're not going to cover them here, but there will be many resources available about GD&T. Go ahead and search the web. I'm planning to do another video, but at this moment, I don't have anything ready right now that I can say, hey, go to the website and check it out right now. But if you're watching this, hopefully I've got something for you to check out on terms of GD&T, but it's a very involved topic. I'm not quite sure how I'm going to handle it yet. So got a little off track there. We have a scale. So next up, we have a scale, which is going to be down here, scale 1 to 2. So when you're looking at your print, how big has the print been made relative to the part? Is it half size? Is it 1 to 1? Is it 2 to 1? Maybe you have a really small print and you're blowing up the views so it's easy to see. But that kind of information helps. Occasionally, you might, as a quick sanity check, you might say, yeah, this part just doesn't match because I can lay it over it and see that it doesn't match. Now, that's not exactly a good way to do an actual quality control check, but it's a great way to communicate a problem. Drop it on top of your view and say, look, it's different. So we always put the scale in there. Sheet size, so we have sheet size A. I made all these prints. Here it is, sheet size A. And so there are different sheet sizes. I don't quite remember all of them off the top of my head, but I know 8.5 by 11 is the A size. So this is the standard American A size, 8.5 by 11. I think it goes to 11 by 17 at the B size. C size, probably 24 by 36, something like that. So they get bigger and bigger and bigger. And D size would probably be 36 by 48, which would be a huge print. Which I used to work with those a lot. I used to work with a lot of big parts that had multiple pages. So we got D size or C size quite often there. And then your standard tolerances. So this is important. Really understand your standard tolerances, because wherever you see a dimension, it'll have a decimal point, 3 digits or 2 digits or 1 digit. It might be a fractional call out. A lot of hole depths are called fractionally. So this is telling you what your standard tolerance is. If it's a 2 digit, you get plus or minus 10 thousandths from that nominal. If it's a 3 digit, you get plus or minus 5 thousandths from that nominal. For any angles, you get 1 degree plus or minus from the angle nominal. And, I skipped the fractional. Fractional and 1 decimal place, you get 1/16. So when you're looking at a print, odds are most of the dimensions on the print will not have a tolerance right next to it. They're all referencing this title block tolerance. That helps keeps the print clean and easy to read. And there will be a few tolerances, usually it's only a few, that deviate from the standard tolerances, and it'll be right next to the requirement. So we're going to go through some of that as well in this lecture series, in this video today. So I would say out of the title block, most important things, first of all, drawing number and revision, and the material and the finish. You want to make sure that they grabbed the right material, they finished it correctly, and the standard title block tolerances. Those are going to be the most relevant to what you're doing every single inspection. The other things are, also important, but you want to, hopefully everything is all, is good in that sense. But every time you pick up a print, you're going to be glancing at material, drawing number, rev, finish, standard tolerances. So title block discussion is over. Let's talk about the drawing views. So when you look at a drawing, it will have standard views that engineers are taught to use. A view looking straight from the top, a view looking from the left sides, view looking from the right sides, looking from the front, looking from the back, and that's what you're seeing on this print. Now, when as an inspector, as a machinist, oftentimes you might get a part that, it's not so obvious what view lines up to what. This one is fairly obvious because it's not symmetric in any way. It's intentionally a little bit odd so that we have a lot of features to inspect. But a lot of parts are symmetric because symmetry is usually great for function. So there's a technique for matching up the views and making sure that the tolerances relative to each other the features relative to each other are correct. So we call it Fishbowl Technique, is what I've heard it called. Basically, you're going to take your part and you're going to match it up with one of the views. It doesn't really matter. You usually start with the front view or the view that has the most features called out, the one that looks like it was the main point of emphasis. And you're gonna drop your part in that same orientation. And as I do this, double check the secondary camera here where you can really see my point of view and what I'm doing if you can't see it on this main camera here. So I'm going to drop that like it's a fishbowl, and then I'm going to assume there's an opening for the fish at the top, just a little goldfish bowl. I'm holding it on the bottom, and let's pretend there's no fish, no water. When we're gonna match it with the top view there, the top view up here. Oops, can't reach it. I'm gonna use the pointer. When we're gonna match this view to this view, what we're gonna do is we're gonna take the part, line it up with the front view, and then we're going to swing it 90 degrees and line it up with the top view. And when you do that, all the features relative to the view should line up. So you go front, you swing it out to get to the top view. To go to the left view, you swing it left. Okay, and you're rotating it 90 degrees, and you just imagine that fishbowl rotating with it to get to the other views, to get to the top view. Sometimes you have to go a couple of rotations because there'll be more views as you go, from left to right. There could be a back view, which isn't shown on this print. So in that case, you'll go one rotation, two rotations, and you would see the back. And if you're checking out this camera, you'll see, what could potentially be another view. So remember, just practice that technique with this part here, the fishbowl swinging back and forth. And it's a great quick check that either the part was made correctly or you're interpreting things correctly. I can't tell you how many times I've seen, a machinist, he's making a part, he's working hard, he's getting, he's making this part, and somehow he just makes it backwards. He did his op 1 right, and then he goes his op 2, and you're like, there's no way I can rotate this around to make all these features fit. Something's gone wrong. And that's just a quick, nice, easy way. Um, one thing you might see is, when you're looking at features here on the print, this print is very basic, and for the most part, every hole is fully located on one view. All the size, all the location, all on one view. But in some instances, some more complex features, you're going to find that one view's got the location, another view's got the size. Maybe one view has the X location, another view has the Y location. As parts get more and more complex, that's sometimes what happens. And so this can be a great way for you to line up, okay, when the feature's here, I know where it is, in XY, then I move it over here, and now I know where it is in XY, and sometimes that will help you fully define the characteristic of the part. So it's a good technique. It's pretty easy once you get the hang of it, and you can do it. I still do it when I get a complex part. I've been doing this for 5 years every day, and I still do the fishbowl on some parts that are really complex. Next up, we're going to talk about notes. So if you're looking at this part, the notes are on the bottom left corner. Gotta spin my mind around. So they're in the bottom left corner of this view, of this print. And notes are kind of just requirements that are really hard to communicate just with numbers, just with dimensions. So, there'll be clarifications or there'll be explanations that you just can't put in numbers. And they'll also emphasize really important areas. Sometimes they'll even a part may called out to be straight with a straightness symbol and a tolerance on, like a standard straightness symbol. But then the notes will also denote, keep this straight. It's important. Maybe there'll be an operational, verify straightness after each operation. Or there may be an operation where it's more susceptible for bending. So sometimes they'll emphasize the critical nature of the part just to help verify everything, help the inspector verify everything's correct in the most critical portions. So in this note, basically I say, part is for training purposes only, right? I created this part. There's no function to it other than for training. So I only put that because if you're going to make this part out of spec, hey, that's fine. There's no spec for this, if you're not going to make it exactly the same, that's fine too. Number 2, I put protective coating is optional. All tolerances apply before coating is applied. I want to take a moment to step aside from this part and talk about the industry. Like I said earlier, I intentionally left a coating off of this print just to make it simpler. It's made out of aluminum or mild steel, so it won't rust. There's no real protection needed. The industry standard, however, is different. I want you to remember that the standard for the industry is if there is a coating, say it's a aluminum oxide coating, hard anodized, that's what I was trying to think of, soft anodized or hard anodized. Well, that adds thickness. These coatings add some thickness to the part, and in the manufacturing world, those matter. Those thicknesses matter. It's not just, oh, forget about it. It won't affect the function of the part. It actually will, with how tight tolerances are. So the industry standard is for all of these numbers on the print to apply with the coating thickness accounted for. So if your coating thickness is 1,000th thick, and perhaps you're going to be putting it on both sides of a part here, you're going to have to account for that in the manufacturing portion of it. So maybe you're going to machine it 2,000 smaller, expecting it to grow when the coating's on. And that can be challenging because all of your numbers, you may be inspecting this before it's coated. So things are going to be smaller or larger. depending on the feature. So um, just remember that if this is confusing you, talk to somebody about it, somebody with a little more experience. But until you experience it a few times, it can be a little tricky to understand. But there may not be a note that calls that out. It's if there's a coding somewhere on this print, odds are that your policy is to machine the part or extrude or whatever processes you're using, and then code it, and then the tolerances apply when the final coating is on. So this part, that's not the case. This part has no coating, so there's nothing to worry about in that sense. If you do want to coat it, maybe you make it out of steel and you want to protect it from rusting, then you're going to add some thickness to that. So that's kind of the purpose of this note here. Number 3, I put tumble finish optional. So, hey, if you want to tumble this thing, make it look a little better, go right ahead, bead blast it, whatever. It's just for training. And then number 4, may substitute plastic material in 3D printing process. Tolerances will be reference only. So most 3D printing applications are not going to be able to 3D print this as accurately as it was machined. So I'm aware of that. I'm just noting it that if you're going to 3D print it, your tolerances are reference, and this is training only. So that's some examples, and some other examples might be, I need you to verify that these two features are concentric within 3,000s, because maybe it's hard to communicate that on the print. Maybe you need a note that says perpendicularity must be maintained, whatever. You just read the notes, it'll tell you everything you need to know. Next up, we're going to talk about the revision block. So on this print, I've got the revision block in the upper right corner, and it just identifies features that have been revised since the previous versions of the print. This print is at Rev A2. So when you are looking at your print, you should see a few of these dimensions that have been changed for Rev A2. And you'll look in the title block, you'll look in the revision block for that. So the revision block, in this case, I went Rev A2, I added a position tolerance on this date in January, and I approved it. So on the title block, on the drawing on the right side here, you'll see an A2, whoops, pointing at the wrong one. On the drawing, you'll see an A2 next to this position tolerance that I added. So that's the difference between Rev A1 did not have any position tolerance, and Rev A2 did. And anything else that I might have revved up, any other features, will also have this triangular revision symbol. There's other revision symbols depending on the software, or depending on the year the drawing was produced. So you just got to get used to it. But generally speaking, it'll have whatever number here is, A2 will match the rev. You may see, if we took this example a little bit further, and 10 years from now, I'm on Rev A5 because I've added a bunch of stuff. But you're going to see A5s on here. You're going to see A4s, A3s. You'll see all of those revs. And then this block here will get bigger and bigger and bigger with each revision that I've put out. So it'll be Rev A2, Rev A3, Rev A4, and it'll just keep growing. You may go to B or C. There's different policies for revving things. But why we do that? You may be asking yourself, well, hey, does it really matter what was revised? I'm going to be checking every single feature against the print I have. Why do I need to call out the ones that have changed? And the simple reason is there's a lot of people involved. There's a lot of hands that touch this. There's an engineer that did the 3D model. There's probably another engineer that did the draft or the drawing. They're not always the same person. There's someone who approved it. There's a programmer that maybe programmed a CNC path or a machine or manufacturing process. There's a machinist that made it. There's a shop foreman that probably took a look at it before it went on the floor. There's the inspector who's checking it. All of these people are looking at the part. So um, when all of these people look at it, do they really want to look at every single revision, or do they just want to look at what changed? Right? If you just look at what's changed, you can update all of your processes just on those maybe 4 revisions or 3 revisions. What I've seen in my career, a lot of times a revision was made by the design team, right? Design says, oh, this part needs to have a change. It's not functioning correctly. We're going to put out this revision. And it's not communicated to the programmer, the person who's writing the program to make the part. So the machinist, he runs the program he's already got. And then the inspector checks it and is like, whoa, something's wrong here. The program made the part wrong, right? Wrong. But it really just made it to a previous revision because it wasn't properly communicated. So these are just inefficiencies. These are not really inspections responsibility. This is a company sort of process that should hopefully be a good one that's fully developed and has a good history. But you want to watch out for those situations. That's why we have revisions. So the programmer, once he does get the revision, he doesn't got to look at every single line of code and look for the changes. He can focus on just the changes that were there. Codes can become thousands of lines long on CNC applications. Same thing with machinists. He gets a print. He's been making the part for years. He's just going to focus on the new parts, on the new pieces. Same thing with the inspector. It's like, oh, there's a revision. All right, I'll really focus on this part and make sure that the revision happened correctly. So it's a real necessary part of communication, teamwork, and quality control. So that's why we use it. Next up, this is pretty straightforward. There's a grid on the title block. So this grid is denoted by the lines on the outsides and some letters A, B, C, D, or 1, 2, 3, 4. You may have more letters as these sheets get bigger. You'll get more numbers, more letters, a larger grid. Sometimes the tightness of the grid, with this example, there's a 16 squares, and you could make it tighter and increase it's a 4x4 grid. You can make it a 5x5, 6x6, whatever you want. But generally speaking, the softwares pick what's standard. So in this case, we have a 4x4 grid, and I drew it up here on the screen so you could see it, but you won't actually see it on a full print. It'll just be on the outside. And so that you can talk about, hey, are you talking about, there's 2 397 holes on this drawing. Which one are you talking about? Are you talking about the one in B2 or the one in C1, right? It's going to be a quick way to identify your features, especially when they're repeated. Distances of 0.500 are all over this drawing. So it can help when you're filling out, inspection sheets. You're going to say, okay, I measure the 500 distance. I use this tool. This is the tolerance that I have. This is the measurement I got. And someone will say, well, which 500 are you talking about? So you can use the grid to call out which 500 you're talking about, usually on the left side of the sheet. So that's one way you can use the grid to help identify locations of things. Here we go. So here's an overlay of that. Everything I was just saying overlaid on top of the grid. Or that you won't see this on the prints, but it's how you use it. So next up, we're going to talk about the feature requirements. So I've highlighted just a few of the features on the prints, but what we call a basic feature is just going to be all of these requirements called out on the prints. Distances, angles, sizes, locations. Nothing that has a special GD&T symbol, like a circle, cylindricity, flatness, parallelism. We're not talking about that. Those are GD&T features, but just the basic features for locating and sizing everything. So I've called out a few, but pretty much everything on here is a basic feature. Now we're gonna stop the video here. It's gone about 35 minutes. So I'm gonna break this up into a few sessions so that it doesn't get crazy long. And we're gonna talk about designer's intent next. So this is kind of a for context, so that you can be a better inspector, a better machinist, so you understand the whole process involved. So I want to thank you guys for watching this video, and please continue with the next ones on drawings, as well as my other ones on gauges and other important topics. Please visit the website pragmaticmetrology.com, and I appreciate you guys tuning in. I'm trying to make these as good as I can, so give a little context to the inspection career, because I'm very passionate about it. I've been doing it for a while now, and I really enjoy it. So hopefully you're enjoying this as well. I want to quickly thank the Laney Machine Technology program. The Laney College has provided this part for me to use, and a lot of the tools in the other videos, and they're a great machine technology program where you can learn about manual and CNC machining, inspection and quality control, CMMs and CAD drawings, 3D modeling, programming, CNC applications, all sorts of things. And they have not only an associate's degree option. If you take enough courses, you can get an associate's degree. You can also get certificates in specific fields. They also have apprenticeships. So they're in contact with local companies and have an apprenticeship program with many of them. And it's a great way to advance your career. So check out, if you're in the Northern California Bay Area, Laney College is in downtown Oakland. It's a great place. Please check it out. And again, I want to thank them. And so please tune into the next video where we will continue about blueprint reading. Thank you.